Hey class, so today's lesson is on the normal distribution, and I wanted to talk about this because it's kind of central, central limit theorem to a lot of statistics. A lot of the statistics we're going to use actually assume a normal distribution, and so I wanted to talk about it for a little bit. It can be confusing to people, and sometimes people make simple assumptions. I'm actually showing a picture of the normal distribution over here on the left, lower left. And you know, typically when you think about the normal distribution, you're thinking about this bell-shaped curve. But it's important to understand what is meant by that bell-shaped curve. So what we're doing with this curve is we're putting observations on this axis, and we're looking at sort of the frequency of them over here on the y-axis. But you know, using those terms and drawing that picture doesn't really describe what it is very well, because if you think about it, if we're going to have some group of observations, they don't make a curve. In fact, if we were to plot them on an axis and just kind of start, drawing from a distribution, and we put the points on the curve on an axis, they don't pile up. So, we're just kind of randomly sampling from a distribution here. For example, we might be making measurements of the height of individuals in the classroom, right? Okay, and we're just putting the points on here. And you see points, there are a lot of points toward the middle, and there are very few short people, and there are very few really tall people. And they kind of get mushed in together here. There are a lot of points that are kind of in the middle. That's not a bell-shaped curve, right? So how does that become that? Well, it becomes that if you think of, instead of on the y-axis being the number of those points, because literally if we were to kind of blow this axis up here and look at just the middle here, what's happening is we're just getting a high density of points in the middle, right? And so you can think of this curve as what's called a probability density function. Those are actually often given the shorthand PDFs, probability density function. So it's really on the y-axis of this curve is the density of points along this axis. Okay, and so if we were to say put these in bins of equal width and count the number of points in these bins, then suddenly we would see that we have more points in the middle bins, right? So if we look at points in bins as a function of the y sub I, so we're putting them in classes now. We're going to get something like this, and so that does look like a bell-shaped curve. And so it's important to kind of understand what this bell-shaped curve is actually telling you. Now, it turns out, of course, there's a nice theory behind all of this, and the theory is not really that important for you to understand, I don't think. But it comes down to this. So Z, which is the probability of obtaining any particular observation. So let's write that out. The probability of obtaining a particular value of an observation is 1 over the standard deviation times the square root of 2 pi times e to the minus 1/2 times the observation value minus mu all over sigma squared. Okay, so this is a mathematical formula for that probability density function, assuming the parametric mean. Well, actually, this doesn't assume the parametric mean is 0, because it's looking at the the deviation from the parametric mean. But this is the parametric mean from which the observation has been drawn. So we have some kind of parametric population, and sigma is the parametric standard deviation. All right, if I'm using this word parametric, what does that really mean? That means kind of behind our sample, we have a normal distribution with a mean, mu, and a standard deviation, sigma. Okay, so a certain number of observations are sigma below the mean, a certain, whoops, sorry, not squared. Certain number of observations are below the mean, certain number of observations are above the mean, etc. Now, why is it important to actually be able to say that something is normally distributed? So, we have this normal distribution, and we're drawing a sample from that parametric population, and we're getting some actual observed distribution, okay? And when we want it, so here's our sample, and it's going to not look perfectly like a bell-shaped curve because it's a sample, right? It's not going to look perfect every time. But we want to actually be able to make the assumption that it was drawn from a parametric population with a normal distribution, because many tests that we do in statistics require a normal distribution assumption. All right, so that's an important part of why we talk about the normal distribution, is that many tests require it. For example, when we do a t-test, we're assuming a normal distribution of the variable that we're doing the test. If we're doing an analysis of variance, we're assuming that the distribution around the mean of a particular group that we've categorized is normally distributed. If we're doing regression and we're doing a least squares fitting of some continuous variable to another variable, we're assuming the y variable is normally distributed about the regression line. And so these very powerful tests rely on the assumption of a normal distribution. And we're going to see then that this is going to be an important assumption, and we need a test for deviation from the normal distribution before we go on and do our statistical tests. Now in JUMP, that is called the Shapiro-Wilk W test, and I'm going to actually cover that in class. And basically what the Shapiro-Wilk W test does is it asks the question, what is the probability that this was not drawn from a normal distribution? And so if W is close to 1, then that's good, and P will be high. In other words, the probability that got deviation from a normal distribution is low, and then W much less than 1, but 2 less than signs here, is bad, and P will be low, indicating significant deviation from normality. So in SAS JUMP, that's going to be our test for normality. And it's kind of an unusual one in that what we hope to find is this one, that W is close to 1 at least, not significantly different from 1, because that indicates we can assume a normal distribution. So unlike most tests where our significant difference is kind of what we're looking for in order to reject a null hypothesis, here we're kind of hoping in a way that we don't reject the null hypothesis of a normal distribution, so that we can go on and perform our tests. All right, but I will go over that in class, how to use SAS JUMP to compute significant deviation from normality. All right, so I wanted to give you that little background on this. if you want to do some more reading on this, I suggest you look at the Khan Academy video on the normal distribution, and you might also do some reading on the central limit theorem. I know you've probably had this in Stat 211 or some other statistics course, but just to remind you where this assumption comes from, that observations or estimates of means will look normally distributed comes from. So this central limit theorem idea. Now, I'm just kind of giving you a preview. When we reject normality, it doesn't mean that we can't do our statistics. What we'll end up doing is some kind of transformation, and I'm going to have a separate video on transformations. So, but this is just sort of a preview to that. When we reject normality, it doesn't mean we are stuck and we can't do our standard ANOVAs, t-tests, and so forth, but it means we're going to have to do some kind of a transformation. Or the other option is we may have to use non-parametric statistics. And JUMP has some of those built into it. So transformations or non-parametric statistics are kind of a solution to the problem of non-normality. But anyway, this is just sort of some background that when we have a continuous variable, we're assuming that deviations around the mean are normally distributed. Now, I will have another video where I talk about the fact that it's actually the deviations around the mean, not the values themselves, that are normally distributed. But I want to give you a quick illustration of that. So let's say we have two groups, and one group has a mean here, x1 bar, and another group has a mean here, x2 bar. Obviously the distribution of observations looks like this. That's not normally distributed. But that's not the assumption of ANOVA. It's actually that the deviations around the mean of each group are normally distributed. So it's those deviations that have to be normally distributed, and that's what we're going to test for deviation using the Shapiro-Wilk W test. Okay, that's it for today, guys. But do some more reading on this so that you can feel really comfortable with the central limit theorem and the normal distribution.